miss the days I could just walk to the market. Because I know like at 8 in the morning, no one would be there. But instead I got a booking appointment in the barber I like, once it goes longer. So now I have to find a different barber. That's my stuff. So sad. This is the last time I did it. Yeah.
Good morning, everyone. Good morning. All right. We're going to continue with fins, which is what we started last class. So I'll very briefly go through the derivation, and then we'll look at different types of boundary conditions for the fins. Okay? So fin heat transfer. The figure we started off last time. So here we have a fin of length, total length L. Okay, this is the location x is equal to 0. This is the location x is equal to L. Okay, and you look at the so this is the net extent. So two things that you've got to keep in mind. One is the end of the fin is called the tip of the fin. Okay, so this is the tip. And the end of the fin where you see that the fin is contacting the wall. So here is the wall. That is called as the base of the fin. So the x is equal to 0 location is the base of the fin. The cross section of the fin, we are going to assume is a constant cross section. So AC is constant for us. And let's say that the perimeter, which I'm going to draw in the darker lines here, perimeter P, which is 2 times the width of the fin times the thickness of the fin plus the thickness of the fin, so 2 times W plus T, where this is W, and then the thickness of the fin is little t. Okay, so that was right here. Little t. So that is the perimeter of the fin. And what we started doing last time was drawing a control volume. Then you take that infinitesimal control volume, look at the energy balance there, write the first law for that. So here is the situation. I'm considering a small element of length delta x along the x-axis. So here is that element, delta x, and then I'm drawing the control volume by removing that out. You'll see that this is the entirety of it. Okay, so I'm going to take that piece out and draw it as a control volume right in the next board. Alright, so this is the situation that we have. And what's going on is that I have my axis system along the length of the fin is the x-axis. And the transverse directions to the x-axis are my y and z, so they are the orthogonal directions. The big difference between a fin and a plane wall, is that in a fin, the direction of convection is perpendicular to the length of the fin. For a plane wall, the direction of convection is parallel to the direction of conduction through the wall. And we wrote this down last time. So for me, the x-axis is the following. X-axis, y, and then z, okay? And then thickness along the x-axis is delta x here. Delta x, and then the total width is w, and then the height of this fin, or the thickness in some sense, is the little t. So I have conduction heat transfer along the x direction. So Q conduction x, and then this heat flows through the fin. We are looking at a cooling fin, okay? So the heat flows through the fin and comes out on the back face as conduction again. X plus delta x, and then we said that there are 4 possible arrows for the convection heat transfer because I have 4 possible surface areas available for convection heat transfer. So one is the top area here. I'm going to call it as Q convection 1, then one in the bottom, Q convection 1 again, because they are in the same direction, positive and negative y-axis, of course. Then along the z, Q convection 2, Q convection 2, okay, so along this area. And then I have the convection 1 along the area that is orthogonal to the one that I shaded, so right here. Alright, and then a basic energy balance, or writing the first law. There is no heat generation within the fin, so my assumptions: steady state, okay, so no time changes coming into play. Then no heat generation within the fin, Q dot is equal to 0. Within the fin, it does not necessarily say that the heat generation within the wall is 0, it's just within the fin, okay. Then one-dimensional heat transfer along length of the fin. And the assumption here is that the length is much larger than the width of the fin and the thickness of the fin. Okay, so here we're going to say that L is much larger than W, and L is also much larger than the thickness. So as long as the width and the thickness are small enough, we can approximately assume that the temperature gradient along the y and the z are 0. And as a matter of fact, the thermal conductivity of a fin is also supposed to be fairly large, and the reason for that is to ensure that the temperature drop across the length of the fin is also reasonably small. If the temperature drop across the fin along the length of the fin is reasonably small, it is approximately as if the whole fin is at the temperature of the base, so that I have the maximum heat transfer possible from the fin onto the atmosphere. Okay, we will look at these subtleties very soon. Alright, so these are our assumptions. Then we wrote down the first law. E dot in, E dot out, E dot generated, is E dot stored. There is no heat generation, there is no storage, because this is all time independent analysis, steady state analysis question.
We say 1 G is along the length. Are we talking only about the
Conduction,
not convection?
not convection. So conduction, heat transfer. So this is conduction along the fin. Thank you for clarifying. In reality, it is 3-dimensional. It is very hard to prevent this from being an approximation at best, but we will live with this. We will proceed with the problem. Okay. Okay. So from here, E dot in and E dot out, I have Q conduction coming in, and then I have Q conduction going out. I have convection in all the four orthogonal directions in the conduction transfer. So I have Q conduction X is conduction X plus delta X, and then I'm going to have 2 times Q convection 1. Notice I'm looking at rate of heat transfer, not fluxes yet. Okay, I have not put the double primes. If I put the double prime, that's a flux. And then I'm going to have 2 times Q convection 2. I'm going to rearrange this and now bring in the fluxes. So this is Q conduction X plus dx, or delta X, minus Q conduction X with a negative sign. Okay, so I'm essentially bringing the Q conduction X plus delta X onto the left hand side and then rearranging the furniture there so that I have a negative sign, and then X plus delta X minus X. And you can immediately recognize we're going to take the limit of delta X tending to 0. And this will eventually give me some kind of a partial derivative with respect to X. And this is 2 times Q convection 1, 2 times Q convection 2. Alright. Then I start expanding Q convection 1 and Q convection 2. So minus Q conduction X plus dx, or delta X, minus that is going to be the following. So watch this carefully. 2 times, big assumption, the convective heat transfer coefficient, I'm going to assume, is the same between the top surface of the fin and the ambient, the side surface of the fin and the ambient, and the tip of the fin and the ambient. We have not reached the tip of the fin yet. I'm looking at the interior of the fin right now. And I'm looking at all the other regions that are exposed to ambient. This is a big approximation. It's not really true. Okay? But we should continue. What we want is an order of magnitude analysis that tells us, it's almost like a back of the envelope analysis. Okay, given a fin with these particular dimensions, given these temperature ranges, given these boundary conditions, what's the heat loss rate? Once you get a ballpark number, then you hop onto ANSYS or one of those finite element or boundary element method programs, and then you start doing the actual analysis. What we are doing is an engineering analysis. Okay? Alright, so this is 2 times H delta T T of x T infinity is the ambient surroundings everywhere. Alright, and then I'm going to have 2 things. The first area is the area of the top surface, which is the width times delta x. And then I'm going to have the side areas, which is the width times the thickness. Okay, so this area here is delta x times W, and this area here is delta x times T. And obviously that factor of 2 times and delta x is a common factor. You rearrange everything, you see that you will obtain the perimeter. Okay, and I'm going to do that in the next step. So take these fellows, do the following. I'm going to take this delta x and bring it to the denominator of the left hand side. Okay, so this is minus q conduction x plus delta x, q conduction x divided by delta x. Delta x is a common factor. This is now 2 times h times w plus t times t of x minus t infinity. there is a hidden assumption here. I am writing the convective heat transfer as T of x minus T infinity, T at x minus T infinity. That is also not the case. It has to be an average temperature along the x direction minus the ambient temperature. But I am assuming that this delta x is such a small element that in the limit of delta x tending to 0, the convective heat transfer can be given as T of x minus T infinity. That's another approximation that we're making. So there are layers and layers of approximation in an engineering analysis. What's our aim is to come up with something simple and elegant so that you can do a back of the envelope calculation. And from experiments it's found out that this is not such a bad idea at all. You're actually getting closer to what the actual experiments also tell you. Okay? Alright, so rearrange it and I have the following. Now take the limit of delta x tending to 0 to conduction x plus delta x q conduction x divided by delta x. Look at this. 2 times w plus t is the perimeter p, so this is h times p times t of x minus t. Alright. We use the same idea for obtaining the heat diffusion equation as well, for plane walls as well as for cylindrical bodies. So this is exactly a similar type of analysis. And in the limit of delta x tending to 0, that becomes a differential quantity. So I have minus dq conduction by dx is h times p T of x minus T infinity. Then we invoke Fourier's law. Instead of q conduction, I'm going to write it as minus k times dt by dx. So this is minus d by dx. Q conduction from Fourier's law is minus k. To differentiate the fact that we have a fin and then we have a plane wall, I'm going to say that this is k suffix f for the fin. This is the Fourier's law applied within the fin. Okay? And this is going to be the area of cross section, which we had labeled there, which is a constant for us. The thermal conductivity is also a constant for us in most of our calculations. Is h times p t of x minus t infinity. And magically this negative sign disappears. K is a constant, area of cross section is a constant. Take all those creatures out. Look at the way I'm going to write it. D by dx, dt by dx is d square t by dx square. Okay, so second order. I'm going to take this kf and then ac and bring it onto the denominator there. Okay, so that's going to be hp by kf ac times t of x minus t. Alright, so we are so far so good, almost there. Look at the quantity in the brackets, in the parenthesis, hp. I'm going to look at the units of this quantity. Okay, so h, an SI system, so watts per meter square Kelvin. What's the dimension of the perimeter? It's the sum of the length, so it has to be the dimensions of length. So this is just meter. Then I'm going to have thermal conductivity, watts per meter Kelvin. Right? And then the area of cross section is meters. The watts cancel off, the Kelvin cancels off. One of the meter square goes off with the numerator couple meters. So this is gone. This is gone. 1 by square or 1 by length square. Length dimension square. quantity has a name, does not have a name per se, but it is denoted by the symbol little m square. Okay, so this entire quantity here, h p by kfac, is going to be called from now on as m square, not to be confused with meter square. Okay, so this is m square. M is a fin parameter. I always fin and pin, they're pretty much the same. You have pin fins, which makes it even more nicer. And not meters. Okay, please make a note of this. And I'm going to do another substitution here, a change of variables. So this is 1. This is an important fin parameter. T of x minus t infinity, I'm going to call it as theta. Change of variables. Call it as a theta of x. This is just to make the writing more simpler. And if I differentiate both sides, t infinity is a constant, so the exact derivative of t of x is the same as that of theta of x. So dt is d theta, and d square t is that. And word of caution, the math is going to get out of hand in a very, very short period of time. Okay? So don't get lost in the equations. What is our idea? Our idea is, okay, I have this fin. Great. So what? I want to obtain the rate of heat loss because of the presence of the fin. That is, if I did not have a fin, what was the rate of heat loss? Just by convection from the wall surface. If I have a fin, what's the rate of heat loss? For that I need to perform all of these, come up with what is called as the fin equation, solve the damn thing, and then obtain, okay, what is the rate of heat loss? To do that, you have to go through a lot of math. That is just the unfortunate business of being in heat transfer. Okay? So we will continue with it with our eyes closed. Instead of d square t by dx square, I actually like this stuff. This is d square theta by dx square, and then instead of hp by kac, I'm going to write it as m square. Bring it on to the left hand side. M square theta of x is 0. The characteristic equation for this is the following. You can do all your fancy Laplace transforms and so on. Not going to do it. Okay, characteristic equation is s square minus m square is equal to 0. S is equal to plus or minus m. So I'm going to expect, if you do the Laplace transform and do inverse transform, you're going to expect an exponential solution. This is the exact opposite of a spring damper system. A spring damper system gives you a sinusoidal solution. A sinusoidal solution implies that you're going to have an imaginary exponent term, e to the power I theta, or e to the power I x. This is not a spring damper system, this is actually an unstable system, if you think of it that way. So the solution is just going to be an exponential decay and an exponential rise. And the two will be competing with each other. Okay? So the solution is theta of x is c1 mx c2 e to the power mx with a negative sign, because I have the characteristic equation written there. And c1 and c2 are to be obtained. Depends on boundary conditions. All right. So fin equation. The summary. Okay, I'm just going to recap that on all this particular panel, I'm going to have the fin equation is d square theta dx square minus m square theta of x is 0, where theta is the following, is t of x minus t infinity. This is just a change of variables, just to make the writing more easier. Little m square is hp by kf ac, where h is the convective heat transfer coefficient, assumed to be the same on all surfaces of the fin. P is the perimeter of the fin. A suffix c is the area of cross section of the fin, and k suffix f is the thermal conductivity of the fin. Okay, and the solution, theta of x, c1 mx, c2 minus mx. Okay, so this is something that we will keep referring back to all the time. All right. Now the first case, to find C1 and C2, I need to look at boundary conditions. Okay, so typically there are two types of boundary conditions that are specified. Actually, four types. I'm going to talk about the first one. So boundary conditions to obtain C1 and C2. First case. I'm going to start off with the simplest of the cases. Okay? In the first case, I'm going to assume that the fin is infinitely long. What is infinite? That's a big question that we need to answer, and we will do that in a while. But because of the fact that the fin is infinitely long, what do you think is going to be the temperature at the tip of the fin? So I'm going to draw it out here. Of course, not infinitely long. L tends to infinity. Ambient temperature is T infinity. What do you think is going to be the temperature at the tip of the fin if the fin is infinitely long? T infinity, right? Absolutely. There's no thinking you know, right? If it is really long, the temperature gradient is going to be much lesser as I keep going further, and it's just going to be T infinity at that point in time. Okay? So I have the first boundary condition at x is equal to L as L tends to infinity, theta of x, which is T of x minus T infinity at x is equal to L, is 0. Why is this? It's because as x tends to infinity, L tends to infinity, T of x at L is equal to T infinity. That's my first boundary condition. My second boundary condition, this is typically prescribed for all the fins, the temperature at the base of the fin will be prescribed. So at x is equal to 0, T of x is T suffix b, little b is the base temperature of the fin. Okay? So the second boundary condition, and x is equal to 0, and it's a simple matter of just substituting these boundary conditions, solving for the coefficients C1 and C2, which gives you a very elegant solution, and which makes complete physical sense. If I look at the temperature distribution along the length of the fin, and if the fin is infinitely long, what type of a distribution do you think the fin should be having, the temperature distribution? Once again, I have an infinitely long fin, an infinite in quotes, I'm trying to sketch the temperature profile along the length of the fin without even solving for these C1s and C2s. What do you think is going to be the general nature of this temperature profile? Exponential decay. There is nothing else to it. You start off at the base temperature. Obviously, I'm going to reach T infinity. It's going to take a very, very long time to reach it. Depends on the rate of decay, of course, which depends on your fin parameters. All right, let's do the substitution. So at x is equal to 0, theta of 0, which is T of 0 minus T infinity. I'm going to call it as theta suffix b, which is this base temperature is the change of variables involved in it. And theta of 0 from the solution, C1 e to the power 0, C2 e to the power minus 0. E to the power 0 is 1, so C1 plus C2 is theta b. That's 1. Then as x tends to infinity, at x is equal to L, theta is T at L tending to infinity minus T infinity. This is 0. I'm taking this and substituting this back into my solution, which I had written down somewhere in the previous panel, if you have been taking down these things. This is going to be 0 is C1 e to the power ml, C2 e to the power minus ml, and now we are stuck. This is 0 here. All I'm doing is, instead of theta, I'm substituting it into the solution for theta of x, which we obtained previously, okay, which is right here. And now we are stuck. So what do? The left hand side is 0. The right hand side contains two terms. One is e to the power ml and the other is e to the power minus ml. And as L tends to infinity, one of those terms drops off, the other term blows up, which automatically should suggest that if this equality has to be maintained physically, which is obviously true, physically as the length of the fin is very long, the temperature at the tip is infinite, T infinity. So if the equality has to be maintained, this term C1 has to be 0. Once again, fin is infinitely long. The temperature at the tip of the fin is T infinity. If I do that and make that substitution, I've done this here, I see that at L tending to infinity, theta is 0. So the left hand side is 0. The right hand side contains a combination of two terms. One is an increasing exponential, the other is a decreasing exponential. For this equality to be satisfied, the only solution possible is that C1 has to be equal to 0. So that as L tends to infinity, this entire thing drops off. Okay, so this implies that C1 is 0, which implies that if I go back here, C1 plus C2 is theta b, substitute. And so C2 is theta b. And so I have a nice solution here. Theta of x. So C1 e to the power mx minus mx. This is theta b times e to the power mx. And typically we write it as a non-dimensionalized temperature. So theta by theta b is e to the power mx. This is infinitely long. Does this make sense to everybody? All right. Then what we want to do is, okay, this is great, I have the temperature profile, it's an exponential decay. What's the loss of heat due to the presence of the fin? What's the heat loss rate? Okay, so heat loss rate due to fin. So in this situation, what we do is the following. I draw the fin. What I am trying to obtain is the heat loss rate. So what is the net heat lost to the ambient? Okay, so this is Q loss. So what you could do is you could integrate through the entire surface area. Nobody likes integration. So we have to come up with a much niftier way of solving this. And the nice way to do this is the following. This is the heat loss rate which is coming out of the fin. Because there is no energy generation within the fin and because everything is a steady state, all the heat that is entering the fin has to be equal to all the heat that is leaving the fin. And all of the heat is entering the fin at the base of the fin, which means that the conductive heat transfer rate into the fin at its base should be equal to the heat loss rate due to convection on the surface of the fin. Okay, so here I'm going to say into the fin I'm going to have conductive heat transfer from the wall onto the fin, okay, and the conductive flux from the wall is the same as the conductive flux into the fin at x is equal to 0, so this is x is equal to 0. This is x is equal to L. So I want to say that Q conduction, the wall, at x is equal to 0 is the same as Q conduction of the fin and x is equal to 0, and because there is no energy generation taking place, this is equal to Q loss. And I want to see if this makes sense to everybody. All the heat that is entering the fin has to leave. The damn thing can't be sitting there idle, right? Heat cannot be sitting idle. It has to go somewhere. And so if I make use of this idea, this is now fairly trivial if you look at it. I'm not interested in the wall. I mean, if I'm given information, I might be, but I'm interested in the fin. So Q loss is equal to Q conduction fin at its base. Okay? Q conduction, we are going to write the Fourier law here. So this is minus K of the fin is the conduction heat transfer rate, so the area of cross section has to come into play. So this is A suffix C. And then I'm going to have d by dx at x is equal to 0. dt by dx is the same as d theta by dx. Theta for an infinitely long fin is defined there, so this is going to be minus kf ac d by dx of theta of x, which is theta b times e to the power minus mx. So this is theta b e to the power minus mx, d by dx of that. And that's going to be minus m times e to the power minus mx at x is equal to 0. And so this is minus kf ac minus m theta b e to the power minus mx at x is equal to 0. E to the power 0 is 1. Okay? And if I rearrange all these terms, I end up getting the following. So Q loss for an infinitely long fin, the negative sign vanishes because I have a minus m inside, so this is now going to be plus m kf ac theta b. The e to the power minus mx also vanishes because I'm substituting x is equal to 0 there. M is defined previously we had defined m square as hp by kfc times a kf times ac, so this is square root hp kfac times kf ac theta b. I have a square root of kf times ac in the denominator. I have something of the same ilk on its numerator without the square root. I can rearrange all of these things and write a very nice nifty equation. Q loss, infinitely long fin, is equal to capital M, where capital M is the formula. And this creature is going to be coming and becoming a part of our equations for the rest of fins, where M is theta b times hp kf ac to the power 1. And if you want on the side, theta b is this is all the stuff for an infinitely long fin. I want to see if there are any questions. So our aim is to calculate this heat loss rate creature. Once we calculate this heat loss rate, then I can find out how effective the fin is. Okay, if I add a fin, here is the heat loss rate. If I don't add the fin, here is the heat loss rate. Take the ratio of the two. If this is a very small number, then I don't care about adding a fin there. That is just a waste of my time and waste of material and intrusion into the space. And that's precisely what we will be doing in the coming few lectures. Okay? We've got to do the same thing for a couple more boundary conditions. And the second one is also fairly reasonably okay, not too complicated. Once again, don't get lost in the math. Your aim is to come up with this guy for different types of fins. And then as a designer, you've taken machine elements, you will have this as a design consideration when you're actually designing the fin. Okay? Alright. Second case. I start off with the solution to the fin equation. And I'll have a list of tables. I'll have a table where we list all these solutions for different types of fins. I just want to derive the first two, and then on Monday or Friday we will solve a problem using the third case. The second case is the base temperature is prescribed. This is typically a standard boundary condition. Temperature at x is equal to 0 is Tb. So theta at x is equal to 0, which is Tb minus T infinity is theta b. Okay? And then somebody came up with this great idea and said, okay, hey, instead of having an infinitely long fin, how about I insulate the end of the fin? What's going to happen? Let's see. The end of the fin, or the tip of the fin, is insulated. When you say something is insulated, what does that imply? No Q conduction, so tomorrow's your exam. dt by dx is 0. Okay, mathematically speaking, right? So dt by dx is 0 at x is equal to L is 0. So let's substitute these boundary conditions and then see what happens to the fin solution. So let's start off with the first one. First one is fairly trivial. So first is theta at 0 is theta b. If I substitute this into the solution, this is just C1 plus C2. Equation 1. Then I have equation 2, which is going to be substitution of the second one. dt by dx and x is equal to L is 0, which implies this guy is also 0, because theta is t of x minus some constant t infinity, so that does not undergo the differentiation. If I do the substitution, so 0 is equal to C1, differentiate e to the power mx, differentiate e to the power minus mx, and then substitute x is equal to L. C1 m e to the power ml minus, because I have an e to the power minus mx, becomes a minus m times C2 e to the power minus m. That's equation 2. And I want to show this one particular case. Okay, this is where we start encountering these hyperbolic cosines and hyperbolic sines. Okay, that's going to be fun. Alright, m is not 0, then you don't have a fin. So I can get rid of m there. So I have the following equation from equation 2. I have C1 e to the power ml is C2 e to the power minus ml, or C1 is a ratio of these two creatures. C1 is C2 ml by minus ml. Do the substitution. So say take this and substitute this back into 1. If I do that, C2 remains the same as before. Instead of C1, I'm going to have plus C2 e to the power minus ml. I think I made a mistake there. This is minus ml, I'm sorry, and plus m. Okay? So this is minus ml e to the power ml. This is equal to theta b. I can solve for C2. Is theta b ml by ml plus minus ml. I'm just taking common factors and then writing this out. Once I have C2, I can find C1. Wait till we get to radiation. Isn't that even better? Okay. So I take this and I substitute this and find out C1. C1 is theta b e to the power minus ml by same thing. And then take all of these fellows, plug them back into theta of x, and we start doing some approximations now. Not approximations, but some substitutions. Theta of x is C1 e to the power mx, C2 e to the power minus mx. So this is theta b minus ml plus mx. The denominator is the same, so I'm going to write that as a common factor. Plus theta b is also a common factor between C1 and C2, so I can take it out. Plus e to the power ml minus mx all by ml minus m. What did I do? I took C2, I took C1, I plugged it back into my generic solution for the fin equation. If I look at C1 and C2, there are common factors, theta b by this denominator, theta b by the denominator. I took that as a common factor out. And then I have the rest of the stuff inside here. And with the last 5 minutes left, I'm going to do the following substitutions. I'm going to jog your memories on hyperbolic cosines and sines. Okay? So cosine hyperbolic x. Anybody? Don't know? Don't want to know? It has to do with exponentials, right? Because we have exponentials, so I'll reduce our misery here. Divided by 2. And if I have sine hyperbolic of x, e to the power x minus x by 2. Okay?